Hello, this is Brother Cromar from the Math Department. This is a continuation of Lesson 18 videos dealing with inference for one proportion. And where we last left off with the sample size calculations. And so what we'll do for sample size calculations for confidence interval. So the next item is just a couple more items when it comes to dealing with confidence intervals. One is that the level of confidence describes the process of creating an interval that predicts the proportion, which is unknown. So approximately 1 minus alpha times 100% of all possible confidence intervals will contain p, which means that if we were to do a gazillion confidence intervals, or I should say 95% confidence intervals, that approximately 95% of those confidence intervals will contain the true proportion, or p. This does not mean that the probability of containing p, the interval either captured it or it did not. So the probability is either 0 or 1. Okay, so before doing a one proportion confidence interval, there are a couple of requirements. First, the data needs to come from a simple random sample. Second, as mentioned earlier, is that the sample size needs to be greater than or equal to 5, so we can assume the distribution of a sample proportion is normal. The descriptive statistics to this would be the sample proportion, which is p hat, not p tilde, but p hat, and then the graphical is either a pie chart or a bar graph. Okay, now here's an example of what a bar graph looks like. This is from SPSS, and this is a pie chart. Now, this is going back to the problem with the Proposition 8, where out of our sample of 1,000, 540 said that they would vote for Prop 8, and the rest would not. And so the green represents those that would vote, and then the blue represents vote for, and the blue would represent those that would not vote for Proposition 8. Okay? So then, so the next item I want to cover is hypothesis testing, okay, for one proportion. Now, there's 5 steps to doing this, and these are similar steps to what you've seen before back in Unit 2. For instance, we state the known alternative hypothesis like we normally do in the first step, but how we write the null alternative hypothesis is different. Now we use the value p. So the null is p is equal to a given value. It could be 0.4, it could be 0.6 or 60%, it could be whatever given the context of the problem. The alternative hypothesis is that it's either not equal to that value, greater than that value, or less than that value. So it could either be a two-sided or one-sided test. Step 2 is calculate the test statistic, and here's the formula for it. It looks a little bit different than what's in the textbook. What I have here is that P naught is equal to the null hypothesis, whatever that proportion is. Step 3 is get the p-value. You can either use the applet or you can use an Excel tool to get the test statistic and the p-value. And then we'll also ask you to calculate the test statistic and p-value, or to illustrate it or to sketch it on your assignments. And then the second to last step, you reject the null if p-value is less than alpha. If not, you don't reject. And then the last step is you state your conclusions. You either have sufficient or insufficient evidence for the alternative. These last 2 steps are the same, okay, that you've seen before in previous hypothesis tests. Okay, so now what I'd like to do is I'd like to go through an example. And here's Billy with his mom, and he's telling his mom, I'm making sure that half of these nuts are peanuts. So he was pretty bored or was getting in trouble, so his mom told him to do something, so he counted peanuts. But he did even more than that, because he is a super crackerjack statistician. He wanted to do hypothesis tests, if you look at the first line here, to determine if less than half the nuts in the can are peanuts, using a level of significance of alpha equal to 0.05. He found that out of 977 nuts, 461 were peanuts, so about 47.19%. So he wants to see if it's less than. So step 1 is the null is that it's equal to 0.5. We want to see if it's less than half. The null is always set to equal to a given value, so p is equal to 0.5. The alternative is that p is less than 0.5 because we're looking for less than half the nuts, and that's right over here on the left side. Okay. The z-scores, we take our p hat, which is 0.4719, minus the null, which is 0.5, divided by the square root of 0.5 times 1 minus 0.5 divided by 977. That's all square rooted to get our z-score, which is negative 1.759. Okay, so then we can go to p-value. We can go to the applet, and the applet, when we go to the applet, it shows. I need to put that in here. So if I put in negative 1.759, negative 1.759, press enter, and we shade to the left because we're only interested in one side. This is the p-value. Okay. We can also get our results by putting in the numbers here where we have, let me go back to the data here, where we have 461 peanuts out of 977 nuts. So if we set the null hypothesis to 0.5, and we want to do less than. So there's three options. We do less than. So we get our test statistic and our p-value here. We can get that using Excel. Okay. So then our p-value, so we can, this is how you could sketch it here. And so since our p-value is less than alpha, which is 0.05, we reject the null, and we would have sufficient evidence to say that less than half the nuts are peanuts. Okay? Now let's go through one more example. So the ability to taste chemical, or PTC, or a chemical PTC, is hereditary. So this is a problem in the online textbook. Some people can taste it while others cannot. The ability to taste PTC is typically, let me expand this here, is typically assessed using paper test strips. When a PTC test strip is placed on a tongue, it will either taste like regular paper or else have a bitter taste. It is assumed that the true proportion who can taste PTC is 70%. A student wants to test to see if it is different using a level significance of 0.05. She finds in her sample that out of 118, 89 can taste PTC. So the null is that P is equal to 0.7 because that's what is assumed. That's the original thought. The alternative is P is not equal to 0.7. So that's because of what we see here. We want to see if it's different. This is how we calculate the test statistic. Here we take 89 divided by 118 to get this number here, minus the null, divided by this value here where it's 0.7 times 1 minus 0.7, divided by our sample size, which is 118, and this is the formula for it over here. Okay, and we get a z-score of 1.286. If we go to the applet and we shade, and shade on both sides, because we're looking to see if it's different, we get a p-value of 0.199. Okay, and if in this case our p-value is greater than alpha, so we do not reject the null hypothesis, and we would have insufficient evidence to say that the proportion of people that can taste PTC is different than 0.70. Okay, so we always refer to the null in the second to last step and the alternative hypothesis in the last step. And finally, on the last slide, before doing a hypothesis test, check the requirements. So first is to check to see if it's a simple random sample, and then the requirement of doing a hypothesis test is to check to see if two values are greater than or equal to 10. If we take sample size times our population proportion, if that's greater than or equal to 10, and if our sample size times 1 minus our population proportion is greater than or equal to 10, if both of those hold, we can assume that the distribution of p hat is normal. And then I'll go to where you can find that in Excel, but the last two items on this is a reminder with the descriptive statistics. For numerical, to sample proportion is what we list, and the graphical is to create a pie chart or a bar graph. Okay, so now what I want to do is go to here. If you look at your Excel output, if you can look at these two numbers, and if they're both greater than 10, then the requirement is met. We can assume the distribution of the sample proportion is normal. Okay, and that concludes part 2 of our lesson 18 video.